Hi there, welcome to this tutorial, which helps you to use RSLogix 500 software, to program some Bradley PLCs. In this video, we'll continue learning instructions which can be divided into move and logical instructions, and program control instructions. Then, we will see how analog signals can be used in our programs. Finally, we'll do a simple project, to read and use a potentiometer voltage. Before we get started with today's video, I just wanted to inform you about all the great content I have been releasing on the plcgoods YouTube channel, which includes industrial automation PLC programming, HMI and microcontroller-based developments. My name is Syed Reza, and if you enjoy this video, I would appreciate it if you could click the subscribe button as well as the notification bell, to receive the latest and the greatest content I will be posting through the channel. Let's start with move and logical instructions. Here, I have inserted a normally open contact. The move instruction is placed here. That's simple. This instruction moves the source value to the destination address. Let me explain how the MVM instruction works. Move with mask. I'm going to use 3 address of the integer files for the inserted instruction. Note that the third integer is 0. Let's compile and test the program on my computer, like previous videos, using RSLogix Emulate 500 software. Well, let's change the CPU mode to run mode. If I enable the inserted MVM instruction, its destination value will change to 3. Why? Let me open the integer data file. Alright, this the source value which must be transferred to the destination address. This the mask value. As you see, only 3 bits of the mask word are 1. So, only 3 bits, bits number 0, 1 and 5 of the source value, will be moved to the destination address. Right? Like sequencer instructions which have been explained in the previous video. As you know, this is the binary form of the number 3. Alright, these are bitwise logical instructions. Let's insert and explain the bitwise logical OR. Similarly, this instruction needs 3 word addresses. Let's compile and test the program on my computer. I have opened the integer data files, to see numbers in their binary form. Before, in the first videos, we have learned OR logic for 1 bit. As you can see, this instruction use OR logic for all 16 bits of source A and B, and save its result on the destination address. Other bitwise logical instructions work similarly. Now, let's insert and test clear instruction. This instruction needs an address like N7:2. If I activate the inserted clear instruction, it will reset its associated address value to 0. Now, let's see what are program control instructions. First, let me insert jump to label, and also, label instructions, to the previous program. Jump to label instruction is paired with the label instruction, by designating the same address to each instruction. First, I want to use a jump instruction in the first rung, which can be enabled by a normally open contact. The inserted jump instruction is used to cause the PLC to skip over rungs. Here, I must write a label. Labels start with the Q letter. Note that I'm writing the program in the file number 2. So, the next number must be 2. Then after colon, a number from 0 to 999 can be entered. Now, let me insert and use a label instruction in another rung, with the same label. Alright, let's compile and download the program to see how the inserted jump and label instructions work. As you can see, PLC executes inserted instructions in the second and third rungs. Well, let me change this number manually. Now, if I enable the jump instruction, then PLC skips over the second rung, and start its work after the inserted label. In this condition, this rung won't be executed by PLC. So, the inserted MVM instruction in this rung won't change the N7:2 address, but the inserted clear instruction in the third rung can reset it to 0. Let's continue with these 3 instructions. Jump to subroutine, return from subroutine, and subroutine label. But what is a subroutine? Pay attention. Until now, we wrote all our programs in the main file, file number 2. Here, we can create another file, divide the PLC program into 2 or more parts, and write them in a separate file. Then call each part of the program from the main file. Let me write a simple program here. First I insert subroutine label instruction. The program is being written here, will be a subroutine, and can be called later, from the main file. Well, I want to use RET instruction, return from subroutine, in the selected rung. Now, let me complete the program. Let me compile the program. Well, here is an error. The first rung doesn't have any output. Let me move the subroutine to the next rung, and delete the first rung. Well, the error has been solved. Now, I want to call the program in file number 3, from the main file. Let me modify this program. I delete the last rung, and use jump to subroutine instruction, instead of jump to label instruction, in the first rung. This instruction, when executed, jumps to the beginning of the designated subroutine file, and resumes execution at that point. Here, I must write the destination file number. For mine that's 3. Let's test the program. Now, only this part of my program is executing. If I enable this contact, program executing will be jumped to the beginning of the designated subroutine file, and after that, resumes execution from this point of my program. Now, this program is executing, so, in the first rung, this contact can activate this output. Another point is about this instruction, return from subroutine. As you see, I cannot activate the second output because of this used instruction. PLC executes the program from the first rung, and back to the main program, when reaching to the first return instruction, or to the end of its program. Alright, until now, we have learned how to skip over a part of a program, or define and call a specific subroutine. Now let me explain a useful instruction which can be used for program debugging. The TND instruction, temporary end, is placed on the right side of the rung. Now, the processor executes the program until reads the end statement. When the TND instruction is activated, it stops the processor from executing the rest of the program. Then PLC updates its physical inputs/outputs, and restarts executing at the beginning of the program. Alright, we have learned basic instructions and features of RSLogix 500 software. Now, let me explain how analog inputs or outputs can be used in a PLC program. Until now, we have done many projects with digital inputs/outputs. In the beginning of this tutorial, we have explained PLC hardware and its wiring. We know digital sensors or push buttons have two states, on or off, or open and close. These instruments use two voltage values to send their states to PLC, also two voltage values are used to turn on/off digital outputs, such as the signal lamp. On other side, there are many devices, such as these two-level, and flow meter transmitter, and also some actuator, which are using analog signals. For example, a voltage between 0 to 10 volt. Other basic signals are -10 to 10 volt, 0 to 20 mA, 4 to 20 mA, and other types of signals. To store and use these signals in the PLC program, we need more than one bit, usually 16 bits. Let's see an example. Suppose, there is a level transmitter to measure level of a substance. This transmitter can be tuned, to generate a voltage 0 to 10, appropriated 0 to 50 meters. PLC can receive the signal with its analog input modules. My analog module model is 1769IF4. These modules give a number from 0 to 3126, according to the received voltage from 0 to 10 volts. But how I found this number? Today's, there is a manual beside each device, and also can be found on the internet easily. See this manual of Allen Bradley Company. In this manual, I can find my analog input module properties. First, let's see its wiring diagram. I will use this diagram to connect a potentiometer to my analog module. Also, this module needs a 24-volt DC power supply to work. This is another wiring diagram. As you can see, it supports both current and voltage signals. Well, this table shows me, the analog module has 4 channels to receive 4 analog signals. And also use a word memory, 16 bits, to store each signal value. Words 4 and word 5 are used to show the states of each received signal. S0 to S3 will be 1 if there is a detected error in each received signal. These bits are using to shows over or underflowing states. Now, let's go to the valid input table. This table shows valid measurement ranges. For example, I'm going to use 0 to 10 volt DC. So, I will have a number between 0 to 3126, based on this setting, in the PLC program. Note that, in the PLC program, we will able to convert the received number to its voltage or level value, using math instructions. Pay attention, analog output modules work inversely. CPU sends a number to the output analog address, then, the analog module will generate an appropriate voltage or current at its output. Now, let's define and do a simple project. I want to develop a PLC program, to read a voltage signal. I have connected a potentiometer to the first channel of the second analog input module. Remember its slot number is 2. The nominal voltage range is 0 to 10 volt DC. Also, I have used a voltmeter to show the appeared voltage on the first channel. Then, PLC calculates the real voltage value. The program can use this formula to convert the received number between 0 to 10. Also, if the voltage value is lower than 2.5 volt, the connected green signal lamp will be on. And if the voltage value is greater than 7.5 volt, the red signal lamp will be on. Alright, let's see my program. First, I have to enable the analog input channel, which is connected to my potentiometer. My potentiometer is connected to the first channel. Here, I must select the analog signal type. Alright, my program logic is simple. I have used division and multiplication instructions, the get input voltage from my 2.0 address, to calculate the real voltage according to this formula, and save the result on F8:1. Then, I have used less and greater than instructions, to compare the voltage on F8:1 address, with 2.5 and 7.5 to turn on green or red signal lamps. Let's test the program. First, let me decrease the input voltage. As you see, when the voltage is lower than 2.5 volt, the green signal lamp will be on. Now, let's increase the voltage to turn on the red signal lamp. Alright, I hope you have learned how to use RSLogix 500 and related softwares to program some Allen Bradley PLCs, like MicroLogix 1500 controllers. In the next video, we'll start learning another software, RSLogix 5000, and other related softwares, which are used to configure and program Logix 5000 family of Allen Bradley controllers. Thanks for watching my content. If you have any question on this topic, make sure you leave them in the comment section below, and if you can spend a few seconds of your time liking as well as sharing this video, if you enjoyed it, that will mean a lot to me. If you have any suggestions for the channel, such as what kind of hardware or software I should be covering, then make sure to leave that in the comment section. See you next time. Bye bye.